Hello, today we are going to talk about enabling OpenCL and SYCL on RISC-V processors. My name is Colin Davidson and I will be presenting with Aidan Dodds. We are both senior engineers at Codeplay who have worked on multiple related customer projects enabling OpenCL and SYCL. In the following presentation we will discuss the following points. We will discuss what Codeplay does and how it relates to this talk. We'll talk about what RISC-V is, why it's important, and how it fits into the ecosystem. We will delve into Codeplay's software stack and look at the technical challenges to support RISC-V, as well as the design that we've come up with to help support RISC-V. We will then look specifically at vectorization with respect to RISC-V's vector extension. Finally, we will look at the next steps. Codeplay is based in Edinburgh, Scotland, with around 80 staff, mostly engineers working on open standards projects. Our goal is to make AI and HPC open and safe to everyone by contributing to open standards and participating in open source projects. The company designs and implements programming models, compilers, and tools for multiple vendors. We enable high-performance compute for different markets, including AI and HPC. In particular for this talk, we do a number of customer projects that involve porting software such as Compute-Orta, which enables customers to be able to enable OpenCL and SYCL, as well as higher level software such as SYCL Blast and TensorFlow. RISC-V is a free and open source RISC-based instruction set architecture which requires no licenses. Because it's open source, there is a very collaborative approach across the community similar to what you see in open source software. There's common free toolchains and a growing ecosystem. There's also new open source architectures being created, such as an open source GPU. It has a very simple, well-designed ISA with about 40 instructions. But on top of this, there are multiple optional extensions. Most implemented ISAs have much more than the base. For example, atomic support is probably a minimum needed for OpenCL. There's also a lot of custom extensions being created. Every implementation can be very different, such as clock speed, how it processes instructions, as long as it implements the ISA in the way it's been designed. Also, they can have a different number of hardware threads, or hearts. There's a growing ecosystem around RISC-V from different vendors. Some companies exist to provide complete solutions, working with clients to design, simulate, and produce the final hardware. We are starting to see more single ISA solutions, with a RISC-V host and a RISC-V accelerator, for example, which potentially makes it cheaper and less complex. It is often used with bespoke IP blocks, such as convolution hardware. It is being used in various research projects. It is growing rapidly. There are over 1,000 members. There are multiple large companies working with it, and Intel recently announced it was going to be fabbing RISC-V. There is growing toolchain support with usable components and multiple simulators being created. It is likely to be used in a lot of new growth areas such as artificial intelligence. At Codeplay, we are great believers that open standards are extremely important in giving a complete, flexible and scalable solution, particularly in the field of AI. RISC-V can be at the heart of that, which is rapidly becoming a mature product through the open source community. There is the potential for lots of accelerators based off the same base ISA. It can scale well up to high performance targets by exposing and taking advantage of processor extensions. The vector extension in particular is important for high performance compute. It can scale up to very large vector sizes. It is well designed for OpenCL and SYCL, particularly the way it does scatter and gather. It can port existing compute-based software to TensorFlow, SYCL Blast, SYCL DNN. They should just work out of the box. This, combined with other software such as OpenCV and Halide, will give us traction in areas such as automotive and AI. The RISC-V Vector extension introduces vector support for all the data types that the ISA supports, such as half, float, or double, depending on what extensions are enabled. Unlike many other architectures, the vector width is configurable at runtime. The extension uses scalable vectors, not int2 or int4, but more like int n. The vector instruction will act on chunks within n, up to the maximum hardware supported vector length width. This is defined as vlen bits. The vector ISA itself is agnostic to this vector length. This can lead to much less bespoke instructions such as seen in other architectures. We can see twice the throughput on one RISC-V Vector implementation with double the vector register width of another. Not necessarily twice the speed overall, as this depends on a lot of factors in the implementation, such as clock speed. This extension is key for us as we want to accelerate using this extension. This extension can simplify vectoring across an unknown number of items at compile time, allowing the removal of scalar tail loops using predication. Also, multiple registers can be combined together to much larger vector types. Let's look at an example to better understand the RISC-V vector extension. As previously mentioned, vector registers are defined as being of vlen bits wide. We will now consider how the same operation may work for different vlen sizes. So in the following example, we have an operation for 15 items. So we configure for this to say that we want a total of 15 elements of 32-bit element size. In the first case where vlen equals 128, this means that you can get 4 floats in a register. So that means that you can write a loop which basically says, I want 15, it returns that I can give you 4. So you do 4, and then you do the further 4, and you do a further 4. And in the final iteration, you're able to get 3. And it does this by creating masking operations on the operation. In the second example, vlen is 256. So in this case, when you ask for 15, it is able to do 8 at a time. And in the following iteration, it is able to do 7 with the final element masked off. I will now pass on to my colleague Aidan Dodds to talk about our software stack.
So I'll talk a little bit about our software stack that we have at Codeplay, known as Acceran. So Acceran is Codeplay's suite of software based on open standards for enabling compute APIs. So it is a hardware-independent implementation of APIs such as SYCL, OpenCL, and Vulkan. So in this context, hardware independence means that Acceran itself is not tied to any specific instruction set. It supports a wide range of different systems, such as CPUs, DSPs, GPUs, etc. And so to make this possible, Acceran has been designed from the bottom up to be highly modular. This is because supporting different APIs requires different and sometimes overlapping sets of functionality. One benefit of this is that an improvement made to one specific module can benefit the entire stack and multiple targets at the same. So an important takeaway here is that Acceran makes it simple to bring these APIs to new targets without sacrificing any performance. Because of this modularity to support new targets, a much smaller amount of code has to be written to facilitate them. So elements of Acceran may run on a host CPU and then offload work to an accelerator-like device. So for instance, this could be a device with programmable cores, at which point we will leverage LLVM to generate code for those cores. Acceran also has facilities to let us use DMA, if that's available, to enhance memory transfer speed. But it's not only limited to programmable cores either. Acceran can also support non-programmable units, such as hard IP blocks. So in this talk, we'll focus on 2 elements of Acceran: compute mux and the whole function vectorizer. So compute mux, which is shown here in blue, is particularly relevant to this talk. So it's a feature-rich abstraction layer. It interfaces other technologies higher up in the stack to the devices themselves, the targets. And these targets might be simulators, FPGAs, or hardware, such as prototype development boards. So in the context of RISC-V, this is where our software stack will interface with the RISC-V hardware. So what is Compute Mux? As I said, it's a feature-rich abstraction layer for interfacing the rest of our stack with hardware, in this case RISC-V hardware. To support a new target and enable all of those APIs, you only need to implement a Compute Mux for that specific system. No other changes are necessary in the stack above. By having a clear layer of abstraction, it solves the many-to-many problem, where you have many different APIs and potentially many different targets, which would exponentially grow the number of code paths that you have to support. So with one point of abstraction, you implement a single Compute Mux and you enable many APIs for that target. So Compute Mux brokers all of the memory access to a device. So for global memory, for instance, it will handle things like allocation, reading buffers, writing and filling them. It also abstracts away kernel operations, such as the compilation of kernels for programmable units and the dispatching of kernels, which might be for programmable units or even non-programmable units. Compute Mux also operates on a command queue principle. So a queue of commands is constructed elsewhere, higher up in the stack, and this is then passed down to Compute Mux, which will then dispatch those operations and hand them over to the device to be executed or actioned. For instance, a command might be to execute a specific kernel, for instance an ND range, which will then be handled entirely by Compute Mux and the result passed back. So typically we've seen Compute Muxes implemented and tailored for a specific system at a time. So when supporting multiple targets, you would have multiple Compute Muxes, one for each. And these might target a specific piece of hardware or a specific simulator. And the phase at which we have implemented these, the system is mostly design locked and relatively fixed. To support RISC-V, however, we require a change of focus. We foresee that it will be much more likely that a Compute Mux will be implemented during the design phase of a system, and that there will really be enough commonality between all these RISC-V targets that it makes sense to have one Compute Mux which is actually able to support many different RISC-V targets. So to support many different targets, this also means that we will have to support many different vendors with different ways of doing things and interfacing to those targets. And each of these targets might have different configurations. And we also want to make sure that it's as easy as possible to support a new RISC-V target whilst keeping any code duplication to a minimum. So in this slide, we'll look a little bit at an example RISC-V system that we might be supporting. So on the left, we can see that there will be some form of host CPU, which may be x86, ARM, or a RISC-V core itself. And this will act as the host. So the main OpenCL, SYCL, what have you, kind of programs will run on this core. And the compute work will be dispatched to an accelerator device. And so this RISC-V accelerator device might have multiple RISC-V cores, as well as potentially some fixed IP blocks, which might be good at doing convolutions, for instance. And the host may have dedicated RAM, the accelerator device might have dedicated RAM, or there may be some form of shared memory between the two systems. So there are a number of technical challenges while we've been bringing up RISC-V support in our software stack. So one thing of note is that some of the RISC-V specifications are being developed while we're undertaking this work, and so it's kind of a moving target. So an example of this is the RISC-V or the RISC-V Vector extension. So this specification is not yet ratified, so it's still currently under work. But we believe this is critical for performance on systems, for compute-like tasks. So we want to try and adopt this as early as we possibly can. So the problem here is that the specification will be updated, and then the simulators that we're using will have to be updated to match the specification. And then the compilers will have to be updated to match the specification. And only then can our software start to take advantage of the compiler and execute on the simulator. So there's a kind of latency there. Another technical challenge is to manage the high kind of configurability between different targets. So there might be processors involved with multiple different extensions. So we need to know about that to inform the compilation phase. So that information has to be passed back up the stack to LLVM. So as there will be lots of different systems being developed by different vendors, that means there'll be lots of different simulators and hardware targets, each with different communication protocols, which we need to try and support. So our abstraction layer has to be capable of interfacing with a wide range of different communication protocols effectively. Different systems will have different memory maps and also a different number of processing units, each with different specifications. So we need a way to hide the details of that and pass relevant information back. So it limits any assumptions that we can make about the target in ComputeMux itself. There are also a number of technical challenges when working with the RISC-V extension, but my colleague Colin will talk about them later. So our initial design for supporting RISC-V targets is to create only one ComputeMux, which will support all RISC-V targets initially. But as mentioned, we do need a way to manage the differences between targets. So for that, we are creating a new abstraction layer to really focus on differences that RISC-V designs have from each other. So one key element here is to hide the details of how we actually interface with the RISC-V device. And so this abstraction layer will also support just the minimal set of features we need for OpenCL and compute languages to be built upon. So really there's a strong focus just on buffer management and kernel management itself. And another design goal we have for this is to make it very easy and quick to support new targets as they're needed. We also want to make it as simple as possible to support different configurations. So a different number of cores, different extensions, and different memory layouts. And so while this abstraction layer is simple, which is good for turnaround time of bringing up a new target, in some situations this also could be a limitation and a hazard to achieving good performance. So we also want to make sure that it is optional, and once a certain maturity is reached, you can step beyond it and start tuning for performance and taking advantage of the ComputeMux abstraction layer, which is much more powerful. So in this slide, we can see some of the Opencl operations that might happen at the source level and how these filter through ComputeMux and become abstraction layer operations. So one of the first things that happen is you're going to do some initialization in your OpenCL code. In order to receive device info, then the abstraction layer will have to provide device capabilities back to ComputeMux, which will then go back through to the OpenCL API. And then perhaps once you've created your platform and devices, then the user is going to try and create buffers to upload data to be worked on. And so creating a buffer will map to an allocation in the abstraction layer. So the device itself might actually just supply a linear memory range, and then the abstraction layer will actually manage allocating blocks of memory from within that range and also handling free as well. So once the buffer has been allocated, then the user may write memory to it. So that's writing from the host onto the device itself. And so that's almost a one-to-one mapping of here's a pointer to host memory and a size. Please write that into the device memory. Then the user might create a kernel itself. So the heavy lifting here is done by ComputeMux, and that's leveraging LLVM to actually do the compilation itself. And so once a binary has been created, that'll be handed to the abstraction layer to the device. So then the next step would be something like CL and QND range kernel. And so a couple of steps here, the work schedule will have to be uploaded to the device. And so that is the details of the ND range to actually work over. as well as an argument pack. So this is all of the arguments that are going to be passed to the kernel, because they need to be accessible on the device when we call that kernel. Then a message will have to be passed across to the device to say, okay, here's some work, please begin. So this will include things like a pointer to the kernel that we're going to execute, along with the schedule and the arts, which have already been uploaded to the device. At this point, the device will then execute the kernel. And so once the kernel has been executed, it's likely that in the source code, they're going to read back the results of that operation via something like clnq read buffer, at which point this is handed over to the abstraction layer, which says, okay, here's a pointer to host memory. Please read so many bytes into that buffer from the device. A lot of the operations that happen at the abstraction layer level are still very high level, which means it's very easy to map this to whatever API the device exposes for sort of interfacing to it. So with this diagram, we can see some of the process involved in supporting a new target for RISC-V. So to bring up a new RISC-V target, we now only need to implement a very small abstraction layer, shown here in pink. And with that, we get a complete working system. So by that, I mean we can run OpenCL and SYCL programs on that target, and they will operate correctly. So this is correctness at the API level. There shouldn't be any missing or unsupported features. So the focus here is on the speed of bringing up that new target rather than the speed of the implementation itself. By shifting focus in this way in the early stages, we can iterate on a system design much, much faster. So this lets the system designers modify and change the design, all while running real-world OpenCL programs and representative workloads for that final system. So they'll get immediate feedback on how well their design is coping and executing those tasks. And so you can iterate on the software at the same time that you can iterate on the design. And so once the design of the system is maturing, then there are a number of options. So you might take the generic RISC-V compute mux and spin that off into one specific for that hardware. And then you might choose to discard the abstraction layer and really focus on all of the flexibility that compute mux gives you to really start tuning for the performance of the target. And so you might then start writing code specifically to target some of the available IP blocks, maybe mapping them to things like built-in kernels in OpenCL. Your chip or system might also support custom extensions, which you might also make available as OpenCL extensions or intrinsics. Also, that's a good time to start looking at and using the system-specific DMA to optimize memory transfers. So the key benefit here of having two different abstraction layers, one highly flexible and focused on performance, and one focused on simplicity and ease of implementation, is that you can really pick where you want to focus your efforts, and you can then have still a rapid iteration time, trying out new features, or you can opt for the complexity and really get performance out of the overall system. So you have the best of both worlds. I'll now pass back to Colin, and he can talk about vectorization.
We will now discuss our vectorizer and how it may be adapted for the vector extension. We'll show how a workgroup could be executed without vectorization, and then demonstrate how this could be vectorized using whole function vectorization. We will detail our current vectorizer and the technical challenges for RISC-V before explaining our design decisions. Firstly, let's consider how we could execute workgroups on RISC-V without vectors. One method is to loop across the various dimensions of the workgroups, executing the work items one at a time, as shown in the diagram. In this case, we have 8 items in the first dimension and 4 in the second. By vectorizing across work items in a dimension, we can use vector support to act on multiple work items at once. In the diagram, we can see 4 work items are worked on at a time. Every operation in the kernel can do work on a vector of 4 values, leading to the use of vector instructions. This is whole function vectorization, and that all of the function can be vectorized at once, rather than just in loops, for example. OpenCL and SYCL are vector friendly across work items, as they are considered to work in parallel. Our whole function vectorizer is part of our software suite. As shown in the previous slide, the purpose is to execute multiple iterations of a kernel in parallel using vectors. It must preserve the same end results as prior to vectorization. It is transparent to kernel programmers who won't directly interact with it. It's currently geared towards fixed width SIMD, although some targets will use heuristics to select the optimal vectorization width. There are several technical challenges associated with vectorization, particularly with RISC-V. The optimal width often can't be known at compile time. A chosen width may not fit the final workgroup size. It may require vector and scalar loops combined to match different sizes. We want to support scalable vectors directly, which we believe will lead to more compact and efficient code. Also, the vectorizer and mask library were originally designed for fixed width vector support. Codeplay felt that fixed width vectors were important to accelerate with this extension. They exist in OpenCL kernels anyway, and current auto-vectorization produces fixed width vectors. This will allow us to get good results early. Also, some cases may be difficult to move to output scalable vectors. We also want to improve the vectorizer for RISC-V so that we can produce fully scalable vectors natively. We want to be able to get this performance without hand tuning or extensions. Part of what we deliver is also a mask library, and this is currently created for different vector widths and can be used in conjunction with the vectorizer. We want to extend this to be able to better use scalable vectors. Looking forward, we want to support additional hardware with bespoke IP blocks such as AI and image-specific hardware blocks or DMA. We want to map OpenCL extensions to hardware. Some may be to help supporting specific features such as DMA. We want to support new or custom RISC-V extensions as needed for new customers. We'll continue to work on the scalable vectors to make this vector extension as efficient as possible. And finally, we will tune for performance. This will vary from chip to chip, but we should be able to do some generic optimization work. In summary, Codeplay are very excited to work on this exciting new growth area. We feel it is very relevant to OpenCL and SYCL, with the RISC-V Vector extension in particular very relevant. Codeplay aims to support many RISC-V potential targets. We want to make this as simple as possible, extendable through abstraction layers. The vector extension is a priority. Thank you very much for attending this talk. We hope you found this interesting.